Hi everyone, I'm Alisa Cherniava. I'm head of research team at NIL Foundation. We're mainly focused on the development of our proof system placeholder, but for a few last month, we tried to combine it with zkEVM type-1. And for today, I want to talk about, firstly, I want to give you some definition of type-1 zkEVM, just remind. Second, I wanted to talk about modularity inside our proof system placeholder. And after these things, I just give you some conclusion. Okay, first of all, I want to remind you what exactly mean type-1. So it would be like full compatibility with Ethereum side, and it would be like the same structure, the same hash function, the same state, all of these things. Also, we keep original gas cost and have full bytecode compatibility. It's pretty obvious. If we have zkEVM type-1, we would have type-2, type 2.5, type 3, type 4. But with each version, we have a little bit downgrade, and sometimes we cannot use all functionality inside EVM. So does it mean like, they give me some simple example. It's like if we can change for another type zkEVM, change hash function and build another Merkle tree, but we cannot link it inside the smart contract to another hash function because, it's pretty obvious. We build it on the top on another hash function. So we try to keep full compatibility with layer 1 application. So also we have a problem inside this thing. So let's try describe it in some not simple words, but it's short representation. It's like we try to prove unlimited instruction in the words of finite circuits. So we would have some program, like here written, we have some unknown length, it can be unlimited, but what is the matter? We have finite set of instruction. So we know what exactly is this instruction, but we don't know how would be length, what exactly instruction would be used, we don't know it in advance. So what we should do, it would be not so complicated algorithm, but firstly we need to split our programs in some several blocks. You can think about it like in the simplest way, it would be one opcode, one circuit. For example, we have exponentiation instruction, we have expectation circuit. But the simplest way, sometimes it's better combine it into some high-level circuits with a similar operation. How we can show it? It would be like memory circuit. It can be arithmetic circuit, which contains inside, for example, some multiplication, addition, and we can have hashes circuits and other things too. So, and the last thing, when we get all intermediate circuits, we need to aggregate it into one proof. We have a pretty obvious technique for this. It's a lookup argument. We have as a result of one circuit its lookup table, and we use it in another circuits. So what's the really problem here? It's a problem what we don't know how to split it into programs, and we don't know how it's better to aggregate it. For now, it's a complicated task. And another one questions, if we have some changes inside EVM, or we have a new cryptographic primitive for proof system, what we can do? We need to, I don't know, write by hand new circuits. What we should do? It's an obvious question, but I tried to answer for them. So I wanted to go to second block of my talk. It's about placeholder. What's it exactly? Placeholder, it's a modular type of zero-knowledge proof system based on block-style arithmetization with custom gates. And I know what you know all these words, except one. It's about modularity. And it means that for now, we have different proof system. And all of them have some kind of constant design. It has one commitment scheme, one field, one of these things. What I try to do, we try to combine all sub-blocks inside the proof system in one proof system. So what we can change? We can change trust assumption. We can change field, lookup techniques, different approach to gate generation, how we can build a recursion. We have a full compatibility with EVM verifier. And also we have different approaches for public input. So how it will be, look like? Like you use our nil tool chain, and you just write your desired properties and get a result. And if you want to another properties, you can just rebuild it. So let's look in the details, what exactly I mean between these parameters. So firstly, it's a trust assumption. Basically, it's just a choice of commitment scheme. For now, we have two options. It's LPC and batch version FKZG. Yeah. For KZG, it's always chip verification, but it has universal trusted setup. For LPC, we don't have any trusted setup, but it's not so cheap, really. But we can achieve some trade-off between proof generation time and verification cost. And when I say verification cost, obviously, I mean cost in gas. Second option, it's a fields, and it's almost based on your previous choice about commitment scheme. So if you choose LPC, you should take some field, and one of factor would be big power of 2. So for this case, we use Palace field, but you can switch it into another fields with property. And for KZG, we can use any field of pairing-friendly curves. So also, we have different lookup techniques. For this slide, I write all of them, but we don't have all of them inside the placeholder. It just maybe you know something about it, but you don't know another one, and it just shows how I try to split it into cases. So, first of all, we have one approach which depends on main assignment table size. Main table size, it's a circuit table, usual circuit table. And when I say it about here, it's lookup table size depend of main assignment table size. Second one doesn't depend. So it looks like what second approach always would be better, but it's required to use field of pairing-friendly curves, and sometimes you cannot do it if you don't want to use non-native arithmetics. So what we have in the placeholder, we have our own generalization on lookup, and for second, we have LSO. Also, we have different gate generation technique. First of all, it's usual Plonkish custom gates like turbo-plonk, just polynomial constraint, copy constraint, all of these things. And the second one, we use IVC Plonkish. It's maybe you hear about like Nova, Protostar, all of these things. And sometimes it's better to use IVC Plonkish, but not always. For example, we say it's about zkEVM, so I try to give you example with of codes. So it wouldn't be better if we use some addition, just simple arithmetic, yes, it would be better to use IVC Plonkish because it's a very small block. But if we think about Kichak, it's pretty big, and if we have a pretty big total amount of repetition of Kichak hash function, you should better to use IVC Plonkish. So, and last two things inside placeholder, it's we have general recursion support. For independable circuits, I mean when output on one circuit it isn't input for another circuit and we do not execute it in parallel, so it's like usual prover. But if we have some intermediate variables, it becomes more complicated, and we need to get a new structure. We call it like a shared public input. So you need to use another Merkle tree for additional columns. It's not so easy, but we have dependable circuit support. And last thing, it's about public input processing. Sometimes we have a big public input, and we can know to send it in the Ethereum directly because it would be cost not so cheap for us. And we use, in this case, hash input. So in the public input, it would be just hash. And we need to prove inside the circuits all Merkle tree from this public input what it exactly has with Merkle root. It's not cheap in the circuit side, and in this case, we need to use recursion support, but it's work. And you would have cheap verification. It was all about exactly proof system parameters, but it's not all about it. Also, we have flexible circuit technique. It's work with zkEVM compiler, and how it's look. We have some trace constraints. It's like usual circuits constraints. Maybe you hear about like gates. They express it like polynomial form, permutation when you have just two cells, lookup when you have some set of cells and you prove what exists in some lookup table. It doesn't matter what exactly, but it's usual our trace constraints. Let me have some metric function, which would be take some set of primitives and would be returns with set of constraints. When I say sets of primitives, it's like you can think about like predefined circuits, something like that. Okay, in the like all algorithm would be looks like this. Firstly, we use zkLLVM. We get some source of C++ code, maybe Rust code, it doesn't matter, and we get a set of primitives like output. After this, we use our metric function, which try to get better. For example, it's try to get better gate degree. It try to get better which cells we need to use, how many columns we would be use. It try to optimize state size, all of these things. So in the second step, we get all these trace constraints and all parameters. After this, we take each primitive. For primitive, it can be like hash circuit, for example. We take hash circuits. We take all these parameters from metric function, and we get some mini circuits. And after this, we get mini circuits from each primitives, combine it together, and we get a result for proof system. We get full instruction in the better way, and it would be created like in automatically. We don't need any handwritten circuits. So let's get me like some results. I tried to say it in some words when I discuss it, but I want to get it you more clear. So look like it this. Sometimes Ethereum virtual machine can be updated. We can, for example, get new opcode, new something, and for now we should to create by some circuit designer a new circuit, and it can influence on all architecture of the zkEVM, and it's not so good. And with our flexible circuit technique, which looks like this, we can load it in zkLLVM without any handwritten circuits and get a result. Secondly, if we have some new cryptographic primitives, for example, like new lookup argument or something else, when we add it in the placeholder, you should just rebuild it. So what I want to say, if we have any changes for proof system, for EVM side, we just need to rebuild it. We don't need to create a new zkEVM. We don't need it. with nil toolchain. And the last thing, it's more minor thing, but I just wanted to say about it, because for now, when we try to build zkEVM, we use different proof system, and how our placeholder is more modular proof system. We just take another parameters, and it gets us usability. So as a result, in one sentence, my final words, with nil toolchain, we can achieve automatic upgradable zkEVM. Thank you. Maybe you have any questions?
I'm just curious, you mentioned so many techniques, but everything relies on zkLLVM. And there's got to be something else. For example, if I change one bit in my computer, it crashes. So is there any research that is just outside of this zkLLVM, relying that two polynomials will differ, etc.? Is there like anything completely different from this, or is all zk based on that?
Could you please repeat about what we definitely talking? I don't hear you.
Oh, you didn't hear?
About exactly gate generation?
No. Just, you mentioned a lot of proofs.
Yeah.
They're all relying on zkLLVM. It's basically how two polynomials of low order will differ if I just change one value and the whole thing crashes. But in my computer, if I change one bit, it will crash too. So there's got to be some other technique outside of polynomial zkLLVM, relying on zkLLVM. Is there any other research? I'm just asking you because you mentioned so many techniques. Have you stumbled upon any?
Yeah. If I understand you correctly, you mean what if we try to create a new thing inside, add new feature? Yes. Add new feature, it would be crash everything. Yes.
No. Are there any other zk proof systems that don't rely on polynomials? Like everything we hear so far, yes. zkLLVM, polynomial, everything. Is there anything else, any other? Yeah.
This side we can't hear well. I don't know why. Okay. It's pretty hard to hear from this side.
Should I repeat again?
You can go to me after this call and we discuss it.
I'll come. Yeah.
Yeah.
We had the same issue before. Now we have the. Okay, but let's finish here maybe and we have Q&A over here. Okay.
Yeah, we can talk here. Yes.